ladies and gentlemen, lizards and ladies, males and ostriches, so on, and so on. Good morning, good afternoon, or good evening, whatever time you are listening to this episode. Today, it is with immense pleasure and profound admiration for human ingenuity that I stand before you to embark on a mesmerizing and in-depth exploration of the captivating world of planes, the magnificent machines that have revolutionized the way we travel, transported goods, and captivated our imagination since their inception. As an engineering topic, planes encompass a vast array of concepts, from aerodynamics and materials science to propulsion and avionics. In the next 40 minutes, we will delve deeply into the rich tapestry of aviation, tracing its roots in history, unraveling the intricate engineering behind these flying marvels, and exploring the relentless pursuit of innovation that propels the industry forward. Our journey through the annals of aviation history begins with the dawn of human flight, a dream that has enchanted minds throughout the ages. For centuries, humans gazed upon the skies, imagining what it would be like to defy gravity and take flight like the birds. From the earliest myths and legends of mythical flying creatures in various cultures to the brilliant sketches and inventions of historical figures like Leonardo da Vinci, the yearning to soar through the heavens has been deeply ingrained in human consciousness. In the ancient myths of Greek civilization, the story of Icarus and Daedalus stands out as a timeless reminder of humanity's fascination with the skies. According to the myth, Daedalus, a skilled craftsman and inventor, constructed wings made of feathers and wax for himself and his son, Icarus. Warned not to fly too close to the sun, Icarus disregarded his father's caution and soared higher and higher, basking in the joy of flight. Tragically, the heat of the sun melted the wax, causing Icarus to fall to his untimely demise. The tale of Icarus serves as a cautionary allegory, illustrating both the allure and dangers of human aspirations to reach the skies. Ancient civilizations across the world were captivated by the concept of flight. In Arabian folklore, the roc, a mythical bird of enormous size and strength, symbolized the mystical allure of the skies. The roc was said to carry elephants high into the heavens, a testament to the awe and wonder inspired by the idea of being soaring through the air. Similarly, in Chinese mythology, the fenghuang, also known as the Chinese phoenix, embodied the ideals of grace and majesty in flight. Often depicted with wings outstretched, the fenghuang was believed to bring harmony and balance to the world. This mythical creature's flight symbolized the lofty aspirations of humanity to achieve greatness through the exploration of the skies. As the millennia passed, the dream of human flight never waned. In the European Renaissance period, the polymath Leonardo da Vinci extensively explored the concept of flight, leaving behind a vast collection of drawings and sketches depicting various flying machines. Although these inventions were never realized during his lifetime, da Vinci's visionary concepts laid the groundwork for future pioneers to unlock the secrets of aviation. The turning point in the pursuit of flight came during the 18th and 19th centuries with the advent of hot air balloons and gliders. In 1783, the Montgolfier brothers, Joseph Michel and Jacques Cayley, launched the first manned hot air balloon flight in Annonay, France. The balloon, called the Montgolfier tilde d'Aérosysterie, ascended to an altitude of approximately 2,000 feet, carrying no passengers but signaling the dawn of a new era in aviation. Following the success of the hot air balloon, inventors and aviators turned their attention to gliders, aircraft without propulsion systems that could glide through the air. One of the notable pioneers in this domain was Sir George Cayley, an English engineer often referred to as the father of aviation. Cayley's meticulous research and experimentation led to significant advancements in the understanding of aerodynamics and the principles of lift. In 1853, he built and successfully flew a full-sized glider with a fixed wing and a tail, demonstrating the feasibility of manned flight. Despite the growing fascination with flight and the remarkable achievements in balloon and glider experiments, true powered flight remained an elusive goal for humanity. The quest to conquer the skies with a powered, controllable aircraft seemed insurmountable, with many inventors and engineers facing countless failures and setbacks. However, it was the indomitable spirit and relentless determination of two brothers from Dayton, Ohio, that would change the course of history and unlock the secrets of controlled and sustained powered flight. Orville Wright and Wilbur Wright, born in 1871 and 1867, respectively, were the sons of Milton Wright, a bishop in the United Brethren Church, and Susan Catherine Coe-Erner Wright. Growing up in a family that valued education and encouraged intellectual curiosity, the Wright brothers developed a passion for learning, experimentation, and innovation from an early age. Inspired by the works of aviation pioneers like Sir George Cayley, Otto Lilienthal, and Octave Chanute, the Wright brothers became enamored with the idea of human flight. They were avid readers and voracious learners, studying the works of these aviation pioneers and immersing themselves in the principles of aerodynamics, materials science, and engineering. Their interest in flight led them to build and fly kites, which served as their initial foray into understanding the dynamics of lift and control. As the Wright brothers continued their pursuit of flight, they began to experiment with gliders, seeking to understand the complexities of aerodynamics and the challenges of maintaining stability and control in the air. Between 1899 and 1902, they conducted a series of glider tests at the sandy dunes of Kitty Hawk, North Carolina. These experiments provided invaluable insights into the behavior of wings and the art of balance and maneuverability, laying the groundwork for their future achievements. The Wright brothers' approach to aviation was methodical and systematic, distinguishing them from many other contemporary experimenters. They designed and built their aircraft based on meticulous calculations and empirical data rather than mere intuition. In doing so, they recognized the significance of both theoretical knowledge and practical experimentation, embodying the essence of engineering. Perhaps one of the most critical contributions of the Wright brothers to the field of aviation was their innovative three-axis control system. They developed a system of wing warping, lateral control, and vertical rudder that allowed for precise maneuvering of the aircraft in flight. By mastering the art of controlling an aircraft's pitch, roll, and yaw, the Wright brothers solved one of the most challenging engineering problems in aviation, maintaining stability and control in the air. On that historic day of December 17, 1903, the Wright brothers' hard work, dedication, and engineering prowess culminated in a defining moment for humanity. With Wilbur observing from the ground, Orville piloted the Wright Flyer, a biplane with a 12-horsepower engine, into the air for a flight that lasted a mere 12 seconds but forever changed the course of history. This first powered flight was a triumph of engineering innovation, transforming the dream of human flight into an awe-inspiring reality. The impact of the Wright brothers' achievement reverberated across the globe, capturing the attention and admiration of the world. Their success heralded the birth of modern aviation, sparking a wave of enthusiasm for flight and inspiring a new generation of aviators, engineers, and dreamers. Beyond their groundbreaking achievement in 1903, the Wright brothers continued to refine and improve their aircraft, conducting numerous flights and experiments to perfect their designs. They developed the Wright Flyer 2 and 3, making longer and more controlled flights, further solidifying their position as pioneers in aviation engineering. The Wright brothers' contributions extended beyond their own success. They actively shared their knowledge and insights with fellow aviators and engineers, assisting and collaborating with other aviation enthusiasts in their quest for flight. Their spirit of collaboration and openness helped foster a culture of innovation and cooperation in the nascent aviation community. The legacy of the Wright brothers' achievements in aviation engineering endures to this day. Their unwavering pursuit of flight serves as a testament to the power of human curiosity, imagination, and ingenuity. Their meticulous approach to engineering and systematic problem-solving continues to be an inspiration for aspiring engineers and innovators around the world. In recognition of their transformative contributions to aviation, Orville and Wilbur Wright are rightfully celebrated as the pioneers of modern flight. Their names are etched in the annals of history, and their legacy lives on in every aircraft that graces the skies. Their journey from humble beginnings to achieving the impossible exemplifies the essence of engineering, the spirit of innovation, and the pursuit of knowledge to overcome the most daunting challenges. The Wright brothers' achievements serve as a reminder that the pursuit of knowledge and the spirit of exploration are fundamental to advancing human civilization. Their legacy inspires us to dream big, push the boundaries of possibility, and embark on journeys that may seem impossible at first. From their modest beginnings in Dayton, Ohio, the Wright brothers' passion for flight ignited a spark that would forever change the world and empower humanity to soar to new heights. The Wright brothers' achievement ignited a spark that soon spread across the world, igniting the fervor of aviation enthusiasts and inspiring a new generation of aviators, engineers, and dreamers. In the years that followed, aviation rapidly progressed, leading to the development of biplanes and triplanes, and paving the way for the use of aircraft in military reconnaissance and combat during World War I. The dream of flight that was once the stuff of myths and legends had become a tangible reality, a testament to the indomitable spirit of human ingenuity and the power of engineering to conquer the skies. As we traverse the corridors of time, we encounter the extraordinary evolution of planes and their engineering. Early aircraft designers and engineers experimented with various wing shapes and propulsion methods. In the pre-World War I era, biplanes and triplanes dominated the skies, with daring aviators pushing the boundaries of flight. Planes rapidly evolved from being fragile and rudimentary machines to more robust, dependable, and capable aircraft, setting the stage for an era of great transformation in aviation. The exigencies of World War I bestowed a new role upon aviation. Combat airplanes played a vital part in reconnaissance, aerial combat, and strategic bombing during the war. Innovations during this period included synchronized machine guns, which allowed forward firing through the propeller arc without hitting the blades. Post-war, aviation's progress soared further, and the 1920s and 1930s witnessed the golden age of air travel. Commercial aviation flourished, connecting cities across continents, and iconic aircraft like the Boeing 247 and the Douglas DC-3 etched their mark in history. The outbreak of World War II set the stage for another period of rapid advancement in aviation technology. Fighter planes like the legendary Supermarine Spitfire and the American P-51 Mustang played pivotal roles in the conflict. Simultaneously, the development of long-range bombers, such as the Boeing B-17 Flying Fortress, demonstrated the potential of strategic air power. Innovation in aviation engineering has always been driven by the demands of warfare. World War II was a turning point for aviation, with aircraft taking center stage in military operations. Engineers worked tirelessly to develop faster, more agile, and potent aircraft to gain the upper hand in combat. The introduction of advanced technologies like turbojets and pressurized cabins allowed planes to fly at higher altitudes, increasing their speed and range. The era of jet engines had begun, and these new propulsion systems were about to revolutionize aviation. The dawn of the jet age marked a transformative era in air travel. The introduction of jet engines significantly increased aircraft speeds, and airlines introduced the first commercial jetliners, such as the de Havilland Comet and the Boeing 707. The iconic Concorde, a supersonic passenger airliner, captured the world's imagination as it brought the dream of faster-than-sound travel to life, exemplifying the cutting-edge engineering marvels of its time. Jet engines revolutionized the aviation industry, enabling faster, more efficient, and longer-distance travel. Engineers faced numerous challenges in developing jet engines, such as handling higher temperatures, improving fuel efficiency, and enhancing safety. The advancements made during the jet age continue to be a cornerstone of modern aviation, with engines becoming more powerful and fuel efficient over time. As the latter half of the 20th century unfolded, aviation witnessed unprecedented progress with the advent of wide-body aircraft, such as the Boeing 747 and the Airbus A380. These behemoths could carry hundreds of passengers over vast distances, making intercontinental travel more accessible than ever before. Advancements in avionics, materials science, and engineering practices further improved safety and efficiency, ushering in a new era of aviation excellence. Wide-body aircraft ushered in a new era of long-haul travel, connecting the world like never before. Engineers worked on designing aircraft with increased passenger capacity, longer ranges, and more luxurious interiors. The Boeing 747, affectionately known as the Queen of the Skies, and the Airbus A380, the world's largest passenger aircraft, exemplify the grand achievements of aviation engineering in the latter half of the 20th century. With the stage set for an in-depth exploration of the world of planes, let us dive deeper into the fundamental principles that govern the engineering of these awe-inspiring machines. At the core of aircraft design lies aerodynamics, the science of airflow and its interaction with solid objects. Lift, the force that keeps planes airborne, It's generated by the shape of the wings and the speed at which air flows over them. Engineers meticulously design wing profiles and study factors like airfoil shapes, angle of attack, and wingspan to optimize lift and minimize drag. Reducing air resistance through streamlined design is essential for maximizing fuel efficiency and speed, exemplifying the relentless pursuit of efficiency in aviation. Aerodynamics, as a cornerstone of aviation engineering, lies at the very heart of the design and performance of aircraft. The interaction between air and the surfaces of the aircraft, particularly the wings, is a complex dance that engineers meticulously choreograph to achieve the delicate balance between lift and drag. Understanding and harnessing the principles of aerodynamics is fundamental to ensuring that an aircraft can conquer gravity and soar through the skies with utmost efficiency and stability. At the core of aerodynamics lies the concept of lift, the force that keeps an aircraft airborne. The shape of the wings, known as airfoils, plays a central role in generating lift. These airfoils are carefully designed and engineered, with subtle variations in their profiles and contours, to optimize their performance under different flight conditions. Engineers employ advanced computational methods, wind tunnel testing, and real-world flight data to analyze and refine airfoil designs, seeking to achieve the perfect balance between lift and drag for each specific aircraft. One of the seminal works in the field of aerodynamics is the work of Sir George Cayley, often referred to as the father of aerodynamics. In the early 19th century, Cayley made significant contributions to understanding the principles of lift and drag by conducting experiments with model gliders. His work laid the foundation for modern aerodynamics and influenced subsequent generations of engineers and aviators. A key concept in aerodynamics is the Bernoulli principle, named after the Swiss mathematician Daniel Bernoulli. This principle states that as the speed of a fluid, such as air, increases, its pressure decreases. This principle plays a crucial role in lift generation, as the shape of the airfoil causes the airflow to move faster over the top surface and slower underneath. This difference in airflow velocity results in lower pressure above the wing, creating an upward force, lift, that opposes the aircraft's weight. The angle of attack, another crucial parameter in aerodynamics, refers to the angle between the chord line of the wing, a straight line connecting the leading and trailing edges of the airfoil, and the direction of the oncoming airflow. As an aircraft alters its angle of attack, the airflow over the wings changes, impacting the lift generated by the airfoil. At lower angles of attack, lift is relatively modest, but as the angle of attack increases, lift grows proportionally, a phenomenon critical for takeoff and climbing. However, this relationship has its limits, as excessive angles of attack can lead to an aerodynamic stall, where the smooth flow of air over the wing becomes disrupted, and lift is dramatically reduced. Aerodynamic engineers painstakingly fine-tune the wing shape and angle of attack to ensure the aircraft's optimal performance across a wide range of flight conditions. This optimization process involves accounting for variables like airspeed, altitude, weight, and center of gravity. Engineers strive to create wings that are both efficient at cruising speeds and effective during takeoff and landing maneuvers. Achieving this delicate balance is vital to ensure safe and stable flight operations in all phases of the aircraft's journey. As an aircraft moves through the air, it encounters another aerodynamic force, drag. Drag is the resistance that opposes the forward motion of the aircraft, and it is one of the primary factors affecting fuel efficiency. Engineers employ various techniques to minimize drag, including sleek aerodynamic shapes, smooth surfaces, and the use of advanced materials. Reducing drag not only enhances fuel efficiency but also allows the aircraft to reach higher speeds with less effort. The study of aerodynamics is not limited to the design of the wings, it extends to the entire aircraft. Engineers analyze the airflow over different aircraft components, such as the fuselage, wings, and empennage, tail section. The interaction between these elements affects the overall stability and controllability of the aircraft. For instance, the empennage, which consists of the horizontal stabilizer and the vertical fin, provides stability and control in pitch and yaw movements. Engineers analyze these airflow patterns to optimize the aircraft's stability and handling characteristics, ensuring a safe and comfortable flight experience for passengers and crew. A key aspect of aerodynamics in modern aviation is the development of high-lift devices, such as flaps and slats. which extend during takeoff and landing. These devices modify the shape of the wing to increase lift at low speeds, allowing the aircraft to take off and land on shorter runways and at lower approach speeds. High-lift devices are essential for the safe operation of commercial aircraft, enabling them to serve airports with shorter runways and challenging environmental conditions. The principles of aerodynamics are not limited to fixed-wing aircraft, they also apply to rotorcraft, such as helicopters and tiltrotators. In rotary-wing aircraft, the design and placement of rotors play a critical role in generating lift and controlling the aircraft's movement in all directions. Engineers face unique challenges in balancing the aerodynamics of rotary-wing aircraft, which require a deep understanding of airflow interactions and aerodynamic forces unique to these configurations. Moreover, as aviation continues to push the boundaries of speed and altitude, engineers encounter new challenges in supersonic and hypersonic flight. At such high speeds, aerodynamic heating becomes a significant concern, necessitating the use of advanced materials that can withstand extreme temperatures. Aerodynamic engineers play a vital role in developing innovative designs to manage the intense aerodynamic forces and thermal loads experienced during high-speed flight. The realm of computational fluid dynamics, CFD, has revolutionized the study of aerodynamics. CFD is a computational tool used to simulate and analyze the behavior of fluid flow over aircraft surfaces. It provides engineers with valuable insights into complex aerodynamic phenomena, allowing them to optimize designs, improve efficiency, and reduce development costs. Aircraft propulsion, another critical aspect, enables planes to overcome gravity and achieve sustained flight. From the early days of internal combustion engines to the advent of jet engines and turboprop propulsion, engineers have continuously strived to improve aircraft performance, enabling them to reach higher speeds and altitudes, thus reducing travel times across the globe. The development of aircraft propulsion systems has been a journey of continuous innovation. Internal combustion engines, which powered early aircraft, evolved into more powerful and efficient piston engines. However, the breakthrough in aviation propulsion came with the advent of jet engines in the 1930s. The jet engine operates on the principle of jet propulsion, using the high-speed exhaust gases to generate forward thrust. Jet engines allowed aircraft to achieve significantly higher speeds, pushing the boundaries of what was previously considered possible in aviation. Safety has always been a paramount concern in the aviation industry. Engineers and researchers continually work on improving structural integrity, reliability, and redundancy in aircraft systems. Additionally, advancements in avionics, the electronic systems that control and monitor flight, have played a vital role in enhancing safety and navigation. The field of aviation safety is built on a robust foundation of engineering principles. Structural engineers design aircraft to withstand the stresses and loads experienced during flight, takeoff, and landing. These engineers use advanced materials like aluminium alloys, carbon fiber composites, and titanium to achieve a balance between strength and weight, contributing to fuel efficiency and range. Furthermore, safety engineers focus on redundancy and fail-safe systems to ensure that critical components have backup mechanisms in place, minimizing the risk of catastrophic failure. The use of advanced materials in aircraft construction has significantly impacted the industry. Materials science plays a pivotal role in selecting the right materials to withstand mechanical stress, temperature variations, and environmental conditions. Composite materials, such as carbon fiber reinforced polymers, CFRP, offer high strength-to-weight ratios, corrosion resistance, and design flexibility. The Boeing 787 Dreamliner is a notable example of an aircraft that extensively incorporates composites, contributing to its fuel efficiency and improved passenger comfort. As concerns about the environmental impact of aviation grow, environmental engineering has become a critical aspect of aircraft design. The aviation industry is actively exploring sustainable practices, including the development of alternative fuels, like biofuels derived from renewable sources. Engineers are also working on noise reduction technologies, aerodynamic improvements, and operational procedures to minimize the carbon footprint and noise pollution of aircraft, ushering in an era of greener aviation. Human factors engineering, also known as ergonomics, is a multidisciplinary field that seeks to understand and optimize the relationship between humans and machines. In the context of aviation, this discipline is of paramount importance as it directly impacts the safety, efficiency, and overall performance of aircraft. Human factors engineering encompasses a wide range of considerations, from the design of cockpit layouts and controls to the implementation of communication protocols and workload management procedures. One of the central objectives of human factors engineering in aviation is to create cockpit environments that facilitate intuitive and efficient interactions between pilots and the complex array of systems and controls they manage. Cockpit design must account for human cognitive abilities, visual perception, and motor skills to ensure that pilots can quickly and accurately interpret information and execute critical tasks. The layout of controls and instrumentation is meticulously planned to minimize the risk of human error and provide pilots with a clear and easily accessible interface. Research studies have highlighted the significance of cockpit design in aviation safety. A study conducted by Prinzel et al. 2010 investigated the impact of cockpit display design on pilot performance. The researchers found that well-designed displays with clear visual cues and organized information led to improved situational awareness and reduced cognitive workload for pilots. This study underscored the importance of human-centered design principles in cockpit layout and the potential for enhancing pilot performance through effective interface design. The concept of user-centered design lies at the core of human factors engineering. This approach places the pilot at the center of the design process, taking into consideration their needs, capabilities, and limitations. Through human factors analysis, engineers identify potential design flaws or challenges that could impact pilot performance, and they iteratively refine the design to create an optimal human-machine interface. In recent years, the advancements in technology have introduced new complexities to cockpit design. Modern aircraft are equipped with sophisticated avionics systems that generate vast amounts of data and present pilots with a wealth of information. The challenge for human factors engineers is to strike a balance between providing pilots with essential data and preventing information overload. Through thoughtful design and information prioritization, engineers ensure that pilots can quickly access critical information without being overwhelmed by unnecessary details. The importance of human factors engineering in aviation safety has been recognized by aviation authorities worldwide. Regulatory bodies, such as the Federal Aviation Administration, FAA, and the European Union Aviation Safety Agency, EASA, mandate that aircraft manufacturers and operators incorporate human factors considerations into the design and operation of aircraft. These regulations aim to enhance aviation safety by minimizing the risk of human error and promoting efficient human-machine interactions. In addition to cockpit design, human factors engineering addresses crew coordination and communication during flight operations. Commercial flights involve multiple crew members working together in a dynamic and often high-pressure environment. Effective communication and coordination are essential for safe and efficient flight operations. Engineers work closely with aviation experts, including pilots and air traffic controllers, to design communication protocols that promote clear and concise exchanges of information. They consider factors such as the use of standardized phraseology, the allocation of responsibilities among crew members, and procedures for resolving conflicts or emergencies. The goal is to minimize the risk of miscommunication or misunderstandings, which can have critical consequences in aviation. Research in the field of human factors engineering has identified the importance of effective crew communication in reducing aviation accidents. A study by Wright and Fauci, 1993, examined the role of crew resource management, CRM, training and improving crew communication and coordination. The study found that CRM training significantly improved crew performance and contributed to a reduction in accidents and incidents. This research demonstrated the positive impact of human factors interventions in enhancing crew coordination and overall flight safety. Another vital aspect of human factors engineering in aviation is workload management. Pilots are tasked with handling and ensuring the safety and reliability of aircraft components requires rigorous testing and evaluation. Materials testing involves subjecting samples to various stress tests, such as tension, compression, and fatigue, to verify their mechanical properties and behavior. Non-destructive evaluation NDE techniques, such as ultrasonic testing, radiography, and eddy current inspection, are used to assess the integrity of critical components without causing damage. Advancements in manufacturing technology have transformed the aircraft production process. Computer numerical control, CNC, machines, additive manufacturing, 3D printing, and automated assembly lines enable precise and efficient production of complex components. These advanced manufacturing techniques result in reduced production time, improved consistency, and enhanced aircraft performance. Flight simulation and modeling are integral to aircraft design and pilot training. Engineers use sophisticated computer simulations to analyze and optimize aircraft performance under various conditions. Flight simulators provide a safe and cost-effective environment for training pilots, allowing them to practice emergency procedures and complex maneuvers without endangering human lives or expensive aircraft. The development of electric and hybrid electric propulsion systems shows promise for short-haul flights, providing quieter, cleaner, and more energy-efficient alternatives to traditional jet engines. Additionally, the concept of urban air mobility, UAM, is gaining momentum, envisioning a world where electric vertical takeoff and landing, EVTOL, aircraft, often referred to as flying taxis, transport passengers in densely populated urban areas, alleviating traffic congestion and providing faster transportation options. Moreover, advancements in space technology are opening new possibilities in aerospace engineering. Space planes, which combine characteristics of both aircraft and spacecraft, offer potential applications for satellite deployment, space tourism, and possibly even travel between planets in the future, manifesting the influence of engineering beyond the boundaries of Earth. The COVID-19 pandemic, which had a profound impact on air travel, demonstrated the resilience and adaptability of the aviation industry. Airlines and manufacturers found innovative solutions to navigate through challenging times, and the experience served as a catalyst for re-evaluating safety protocols and travel practices, illustrating how the aviation industry, guided by engineering expertise, responds to unforeseen challenges. As we look ahead to the future, the aviation industry faces exciting opportunities and significant challenges. The demand for air travel continues to grow, necessitating more sustainable practices. Engineers will play a crucial role in developing innovative technologies and designs to make aviation greener and more efficient, driving the relentless pursuit of engineering excellence. Artificial intelligence, AI, and big data are emerging as key players in the aviation industry. AI-driven algorithms analyze vast amounts of data to optimize flight routes, predict maintenance needs, and enhance safety. Big data applications provide valuable insights into passenger preferences, enabling airlines to tailor services and improve customer experiences. Supersonic travel is also making a comeback with advancements in supersonic aircraft technology. NASA and various aerospace companies are exploring the possibilities of supersonic flight while addressing the challenges of noise pollution and fuel efficiency, signifying the revival of engineering innovation. Moreover, unmanned aerial vehicles, UAVs, and drones have transformed industries such as agriculture, surveillance, and logistics. Engineers continue to enhance UAV capabilities, develop autonomous systems, and refine air traffic management solutions to accommodate the integration of drones into our airspace, showcasing the impact of engineering on diverse sectors of society. The concept of the Internet of Things, IoT, has also found its way into aviation. Smart sensors embedded throughout aircraft collect real-time data, allowing for predictive maintenance and early detection of potential issues. IoT-enabled connectivity on board aircraft enhances passenger experience and supports communication between aircraft and ground systems, exemplifying the convergence of engineering and digital technologies. Cybersecurity has become a critical concern in aviation, with an increasing reliance on interconnected systems and data networks. Protecting aircraft from cyber threats becomes paramount. Engineers and cybersecurity experts work together to implement robust safeguards and encryption protocols, highlighting the interdisciplinary nature of modern engineering challenges. In today's digital age, where the world is interconnected through sophisticated networks and technologies, cybersecurity has emerged as a critical concern across various industries. including aviation. With the growing reliance on interconnected systems and data networks, the aviation industry faces unique challenges in safeguarding aircraft and flight operations from cyber threats. As airplanes become more connected and reliant on digital technologies for navigation, communication, and system control, the need for comprehensive and robust cybersecurity measures becomes paramount. The interconnectedness of aircraft systems and the broader aviation infrastructure creates an expanded attack surface for potential cyber adversaries. Any vulnerability or compromise in the network can have far-reaching consequences, compromising flight safety, passenger data, and even national security. Therefore, aviation engineers and cybersecurity experts collaborate closely to devise innovative solutions that protect against cyber threats while ensuring the seamless functioning of aircraft systems. One of the significant challenges in aviation cybersecurity lies in the diverse array of interconnected systems on board modern aircraft. These systems range from avionics and flight control to in-flight entertainment and passenger communication systems. Each system may have different vulnerabilities, and securing them requires a comprehensive understanding of both aviation engineering principles and the intricacies of cyber threats. To address these challenges, aviation engineers and cybersecurity experts adopt an interdisciplinary approach, combining their expertise in aviation, computer science, software engineering, cryptography, and network security. This collaborative effort involves conducting thorough risk assessments, threat modeling, and vulnerability analyses to identify potential weak points in the aviation ecosystem. Engineers work tirelessly to implement robust safeguards and encryption protocols to secure critical data and communications between aircraft systems and ground-based operations. Encryption techniques ensure that sensitive information remains confidential and cannot be intercepted or tampered with by malicious actors. Secure data transmission protocols, such as Transport Layer Security (TLS), are employed to protect communications, minimizing the risk of data breaches and unauthorized access. Moreover, aviation engineers emphasize the principle of defense in depth, which involves deploying multiple layers of security measures to protect against potential cyber attacks. These layers include firewalls, intrusion detection and prevention systems, access controls, and continuous monitoring. This multi-layered approach ensures that even if one security measure is compromised, other layers remain intact, mitigating the impact of potential breaches. In addition to securing onboard systems, aviation cybersecurity extends to safeguarding the communication networks and data centers that support air traffic control, flight planning, and aviation infrastructure. These critical components of the aviation ecosystem require constant monitoring, threat detection, and response capabilities to protect against cyber incidents that may disrupt air traffic management or affect the integrity of flight operations. Regular audits, security assessments, and penetration testing are conducted to evaluate the effectiveness of cybersecurity measures and identify potential areas for improvement. This proactive approach helps in staying one step ahead of emerging cyber threats and adapting security protocols accordingly. Furthermore, as the aviation industry continues to evolve and embrace emerging technologies like artificial intelligence and the Internet of Things, (IoT), the complexity of cybersecurity challenges will also increase. Engineers and cybersecurity experts must remain vigilant and proactive in adapting their strategies and techniques to address evolving threats and vulnerabilities. To enhance cybersecurity awareness and knowledge within the aviation community, industry organizations and regulatory bodies, such as the International Civil Aviation Organization (ICAO) and the Federal Aviation Administration (FAA), collaborate to develop and disseminate cybersecurity guidelines, best practices, and standards. These guidelines serve as valuable references for aviation stakeholders, including airlines, aircraft manufacturers, and service providers, to strengthen their cybersecurity posture. Moreover, research institutions and universities actively contribute to the advancement of aviation cybersecurity. Academic studies and research papers explore emerging threats, vulnerabilities, and mitigation strategies in aviation cyber domains. For example, research may delve into the analysis of potential cyber attack scenarios on aircraft systems or the development of novel cryptographic algorithms to enhance data security. To bolster cybersecurity expertise in aviation engineering, educational programs and certifications in cybersecurity are increasingly becoming available to engineers and aviation professionals. These programs equip them with the necessary knowledge and skills to implement robust cybersecurity measures in aircraft design, maintenance, and operations. In conclusion, planes represent one of humanity's most remarkable engineering achievements. They have transformed our world, connecting people and cultures, enabling global trade, and pushing the boundaries of exploration. The relentless pursuit of innovation in aviation engineering has given rise to safer, more efficient, and environmentally conscious aircraft, symbolizing the enduring impact of engineering ingenuity on human progress. As we continue to explore and innovate, let us remember the pioneers of flight whose dreams and determination paved the way for the marvels we witness today. Let us also acknowledge the dedication of engineers and aviation professionals worldwide who work tirelessly to ensure that air travel remains safe, efficient, and accessible to all, celebrating the unwavering spirit of engineering excellence. In this never-ending quest for excellence in aviation engineering, the sky is not the limit. It is merely the beginning of a journey towards a future where dreams soar on the wings of innovation. Thank you for your time, and I'm open to any questions or further discussions you may have. Just make sure to leave them down in the comments below. Leave a like, leave a follow, leave a comment, and so on. Have a good one all.